So, in today's lecture, I am going to talk about the language, notion, and basic concepts of system theory. If you see the investigation of optimal control, then that is based on the mathematical model expressed in state space form. And if you see the generalization of state space form or their related concepts, that is basically covered by the system theory. So in this course, we are not going to summarize all part of system theory, but just I am going to take those parts which is quite useful to understand or design or do some kind of analysis for optimal control problem. So let us start the today's lecture. So most of time whenever we are talking about the control problem, at that time I have certain kind of physical object. After that I have clear cut objective, and we, in order to achieve that objective, we have to design some kind of subsystem, you can tell, such that we can achieve that particular specified objective. So in this particular example, I have started with very simple physical object, that is called inductor. And in this particular platform, since real inductor is not available, due to that reason what I have done, I have represented that particular inductor using some kind of symbolic form. So here you can see that this is the symbolic notion of the inductor. I hope that you all are already well aware about the basic idea of the resistor, inductor or capacitor. Due to that reason I have selected this element. And if you see here very much carefully, so if I current, and which is varying with respect to time, if that will pass through this particular inductor, then I can relate the voltage and current across this inductor L by using this kind of differential equation. This is called differential equation, L dit by dt equal to Vt. For simplicity purpose, if you put L equal to 1, then I have this kind of equation. So what we are telling that I have initially, this is my physical original object, and after that I have captured that object using some set of mathematical differential equation. So now this object is no longer a physical object, this is some kind of abstract object. And for abstraction we have used the idea of calculus. Now what we are telling that whatever behavior of this abstract object, I am going to match with the physical object. Now similarly, so I can able to give some kind of abstraction. Abstraction means it is possible to show that various objects can be captured using this kind of differential equation. And here for simplicity I am assuming that whatever input, here you try to see that what is your input and output, so you can interpret based on your convenience. You can tell that okay, I have applied some voltage Vt and I am going to measure some kind of current It across this particular inductor. So in that particular situation I can interpret Vt as some kind of input. and IT as a some kind of output. And if you clearly analyze this, then input is somehow some kind of real valued function. It means that V and T is the argument, so R some real number, and again that is going to generate some kind of real number. So basically Vt represent some real valued function, and similarly I am telling that It also going to do same kind of things. They are going to map some kind of real number, and basically time is associated, so you can also assume that time is positive in this way. And if you generalize this, then we are getting this kind of expression. It means that Yt again belongs to some kind of real number and Ut belongs to some kind of real number. So I have object, I have input, and I have certain kind of output. And after that, you can see here that I have drawn a geometrical picture. And what we are telling that if I have certain kind of object which has certain kind of special property, what kind of special property? I am telling that if I give some kind of real number as a input, and if I will get some kind of unique real number as a output, or if I will give some kind of real valued function, and if I will get unique real valued function as a output, then this particular object is called a system. So, so we are only define system if our output is unique. And this is the space. What is meaning of a space? You can see that whenever we are doing abstraction, then there is no limitation on the input and output. But most of time whenever I have physical object, I have taken physical object as a inductor. You are already well aware that I cannot able to apply any amount of current, or I am not able to pass any amount of current through the inductor. There are always certain kind of limitation, and basically this particular part is represent the limitation, and that is called input output pair. It means that for abstraction I can tell that input and output is anything, but in practical situation that is not the case. I have always certain kind of limitations, and I have actually capture that space using some kind of Cartesian product. So this represent Cartesian product. So I have certain kind of relation between input and output, but this relation is always unique, and due to that reason this represent certain kind of function. So whenever we are talking about engineering system, that represents some kind of function, and it means that whatever input and output, that is going to lie only in this product space, and whatever value, that is called input output pair. Now let us try to understand one more thing, that is called the state. What is basically a state? So suppose you have some kind of system, then what is our goal? Our goal is to predict the future. And what is future? That is output. So in order to predict the output, I need the input, and after that if you start experiment at t0, so always some kind of memory that is associated with that, and if I know that memory and input, then it is possible to get the output. That kind of memory you are also able to visualize from here. If you write like this, dit by dt equal to vt, then you can see that if you integrate this particular quantity, then I can further write like some quantity like this it, and that is nothing but I have to integrate this v tau, and after that d tau, and after that what I have to do, I have to do this kind of integration from minus infinity to t. And suppose t is the time of experiment, then I can write like this T0 V tau d tau, and after that I have T0 to T, and after that this is V tau d tau. So this part is somehow the memory or some kind of initial voltage when you are going to start the experiment, and this is called the state. So a state is some kind of, you can assume some kind of variable or some kind of physical variable that will carry the information of all past events. That is the meaning. Now let us try to understand what is meaning of input output pair in this particular abstraction. So I am representing the U. I have already told you that U I can apply or I can select from a space of continuous real valued function. Real valued because all instrument whatever we have developed, that is only able to understand the real data, and this ut is input, and since dy by dt we are telling that in this way I have related my input and output dy by dt by dyt dt equal to ut, and due to that reason I have this kind of relation. So this particular quantity alpha is summarize the all past memory, and somehow if you interpret this very carefully, then that is the state of the system. So I have just talked about the input output pair in this particular time interval. Now if you see that I can write the proper definition from system theory and after that explain everything, but this kind of things requires a lot of time. Already I have recorded lecture of mathematical control theory, so those who has interest, please go through YouTube channel and please see the all detailed lecture. But in this particular lecture I am just going to give the overview. So most of time I will take some examples, and using examples I am going to talk the notions, language of system theory. So in order to talk the another some kind of important quantity which is quite useful to denote the any problem related to system theory, or you can tell optimal control, what I am going to do, I have selected some object, and after that I am telling that this object is only moving in one dimension, and I am going to apply some kind of force ut, and this is mass mt, and after application of force this object is going to change their position from origin to some point xt. So you can, using Newton's law, you are able to come up with this kind of mathematical model. So I hope that you all are well aware about this. So m, and this is acceleration d to xt by dt square equal to ut. I am assuming here that whatever mass, that is point mass, whatever this displacement, that is two time differentiable. Now with help of this particular mathematical model I am going to understand the concepts of a state, what is output, what is order of system, what is importance of system's initial state, because if you are not able to see carefully these kind of things, then you are always facing difficulties. So with this example I am going to tell you the story, and these terminology are frequently used in any control problem. Either you can talk about classical control, you can talk about modern control, you can talk about optimal control, digital control, robust control, everywhere. So this is the common terminology. So now let us start case by case. So what I am going to assume that whatever system I have taken, means I have taken one mass and that is moving from one point to another point. So case 1, I am going to define the output. Basically output is always decided by the users. So user can choose any output. So I have first selected that position variable as a output. In case 2, I have selected the velocity variable as a output, and after that In case 3, I am going to concern with both position and velocity. So you can interpret like this, that you are driving a car, so you are just interested in the positions. Someone who loves driving car with very fast, they are also concerned with velocity, and someone is interested in both. So try to understand that how these four things: state, output, order of system, importance of system, initial state is associated if I fix the case 1. So first try to understand the input output model. So basically, if you talk about input output model, then first I have to understand what is my output. So we have, this is actually decided by the user. So user has thought that, okay, I am going to go with the position, and due to that reason this as a output. And in terms of output, now you can see that I have mathematical model, that is m d2xt by dt square, that is equal to ut. So y equal to x, just you can substitute here, and in this way I can able to relate input, and this is our output. So basically, with respect to input and output, you can see that here 2 will appear, so I have second order model. Now let us try to come to the second case, because just I am going to see the order of model and how basically input and output is dynamically related. Dynamically related means, since differential equation comes into picture, so in order to understand output y2 yt, I have to understand the control as well as initial condition. And after that, if I fix the y equal to x dot, now you can see that since x dot is already here and my equation is m d2 xt by dt square equal to ut, and I can also able to write this as a dx dot t by dt equal to ut. So just what you have to do, you have to substitute here x dot in place of x dot, you can just substitute u, and if you just concern with the velocity, now you can see that your first order model is changed into second order model. So my original model is not going to change, but if you are selecting the output, different output, then based on the selection of output, your order of system or order of model will also change. So that kind of message I am going to give you. After that, let us come to the third case, where I am assuming that I have output as a position as well as the velocity. So both I am assuming as a output. So in this particular case, you can see that I have, with respect to first output, I have second order system. With respect to second output, I have first order system. So basically, if you see the overall order, then that remains the second order. So in this way, by selection of the particular output, you can see that in some case, for the same system, order equal to 1 and order equal to 2. So due to that reason, you have to very much careful with respect to selection of the output. Now let us try to come to the state space model. So whenever we are talking about state space model, most of time we are try to consider all physical variable. So you try to understand what is the physical variable involved in this problem. So basically, mass is moving from one point to another point. So two quantity obviously comes into picture. So one quantity is position, another quantity is the velocity. And due to that reason, what I am going to do, that I have selected the two quantity, and that two quantity is position as well as the velocity. So now you can see that second order differential equation m d2 xt by dt square, now that is converted into set of two first order differential equation, and here output y equal to x1. So here x1 is, you can see that if you do not know the initial condition of x1 and x2, you are not able to solve this particular differential equation. So somehow I am telling that x1 variable is going to carry all information, all past information, and these two are the states of the system. Now try to come to the second one. So one can also select a state like this. In place of x1 equal to x I have selected, someone might tell that okay, I will not select x1 as a x, I will select by some kind of a scaling, and I will select some other kind of a scaling. And again you can see that I have some kind of differential equation, first order differential equation or set of first order differential equation in terms of x1 and x2, and output here now also altered. It means that now if I have same system, then I can able to choose different space state space representation. And due to that reason, a state space representation is not a unique representation, that is non-unique representation. Now let us come to the second situation, when I am assuming that my state or my state x1 is dx by dt. So in this situation I have system representation, state space representation is like this. So I have one kind of algebraic equation in terms of output, and I have first order differential equation. So if, since I am assuming that y equal to x1 as my output, that is velocity, and due to that reason this is the state space representation. But here you can see that from this equation I cannot able to determine the position. Why? You try to understand this fact, that you are able to understand the x1, and if you are able to understand the x1, then x1 is velocity. In order to know this x position, you have to do integration. So obviously if you do not know the initial value of x, then some integration constant comes into picture. So from this relation I cannot able to uniquely determine the position, and due to that reason I have told you again that whenever you are selecting the output, please be careful, because if you select output as a velocity, you are unable to keep track on the position. And due to that reason people are suggesting that you try to select the proper value as a output, and you try to see the proper state space representation. After that let us try to come to the third case. So in third case I need everything as a output, so I can represent like this. So in this representation you can see that if you multiply this with this, then y equal to x1 and y2 equal to x2. So both are output, and you can now select any mathematical model, because obviously you need two mathematical model, means output, on output you are selecting x1 and x2, so you cannot able to select only one state as a velocity. You have to select position as well as velocity. And in that way, alternatively, if I select the another state space representation, so correspondingly my output is represented like this. So by manipulation you please check that why this kind of things comes into picture. Now I am going to talk about some kind of remark. So what we have seen that I can select either position as a state variable, or position as a output, or velocity as a state variable, velocity as a output, and after that I can represent the differential equation. So whenever something as a state variable, they are carrying the information of past, and whenever we have system, then we need minimal set of state variable. It means that if something is completely determine the other, then we are going to reject that. Suppose that one can argue that why I cannot select acceleration as the state variable. So you can see that if you know u, control input u, so m x double dot d2 x to dt and ut. So if you know ut, then directly there is no need of any history. If you know mass, you know ut, you are able to directly calculate the x dot, and due to that reason x double dot is not the state variable, or inside a state vector I am not going to consider x double dot. So, and I hope that this kind of things is already clear to you. So but just I am going to clarify that how basically one can select the state, how basically one can select the output based on the problem statement. And after that, what we have observed in this particular example, that a state vector is a list minimal set of variable that completely determines the dynamic state of system. So from output, that is not possible. Sometimes if differential equation is just written in terms of output, and we have seen that if I select output as a velocity, then I cannot able to determine the position uniquely. So due to that reason, now in order to understand whole system, I have to understand about each and every state variable, and we have to put that state variable inside a vector, and we have to make sure that that is minimal set. And in this particular example, I have told you that minimal set is position and velocity. And how to select minimal set? After that, I have already told you that minimal set means other variable cannot express in the linear combination of the remaining variable. That is the meaning. A state vector is not unique. Many choices are possible for a given system. So system is fixed, but I have infinite many choices. So I have shown just two choices, but by scaling you can select any other choices also. And due to that reason, we are telling that I have many choices, and that is not unique. And this non-uniqueness is very much useful. And due to this non-uniqueness, I will tell you several stories that you can able to express complicated system using some kind of system where we have less complication. After that, you try to see that output variable can be completely determined from any such choice of state variable. So you can select any state variable notion, but you are able to determine the output. A state variable may or may not have physical interpretation. Sometimes, most of time, people are selecting a state variable, and a state variable has certain kind of physical interpretation, but most of time it is possible to show that we don't have any physical interpretation. But please do not worry about that. Now let us try to see another example, and again with another example we are going to see that how one can represent the different kind of mathematical model. So I have selected again one circuit from the electrical engineering. Why I have selected this circuit? So even if you don't have basic idea of electrical engineering, but during 10 plus 2 physics you have already learned about the RLC network or some kind of RLC combination, and what is effect of the voltage or this kind of things on that. So here you can see that I have selected different kind of resistor. So this resistor is fixed resistor, and after that this resistor is actually time varying resistor. Actually if you see the resistor, so as temperature will increase, it is possible to show that some resistor doesn't remains, the resistance doesn't remains the same, that is increasing. And due to that reason one can assume that some resistance is changing with respect to time, and whenever some resistance is changing with respect to time, then people are using this kind of notion. So here I have certain kind of inductor, here I have certain kind of capacitor, and after that here you can see that this resistor has another property. So this resistor is actually changing with respect to time, and this resistor is called non-linear resistor. It means that the current and voltage characteristic of this particular resistor is no longer the linear, because from Ohm's law most of time you are already well aware that if I apply some voltage across resistor, then that is proportional to current. But in non-linear resistor that is not the case. So I have three different kind of resistor here, and here all resistor is somehow some kind of static element, that is no longer a dynamic element. So what is meaning of a static element? If you apply something, then that is reflected, but that is not going to depend on the past or future. But if you see the capacitor or inductor, that is not the case. They have always some kind of a storage inside that. So if you are not going to take care about that storage, then some difficulty comes into picture. And I have already told you that whenever we are talking about the state space, at that time that is somehow related to the some kind of element which is going to carry the information. So here I am going to assume that capacitor is going to carry information in terms of voltage, and inductor is going to carry information in terms of current. And due to that reason, in this whole circuit can be represented by second order model, and this is the voltage source. So I can apply Kirchhoff's voltage law and Kirchhoff's current law. So just I am for sake of revision, if you move in some loop, then voltage drop, final voltage drop from here to here, that is equal to 0, summation of all equal to 0. And if you are here, then incoming current is equal to outgoing current. So in that is the intuition, or you can also understand in terms of conservation of energy, that whenever you are going to see here, then what happens, that whatever charge that is going to enter here, so same kind of charge is going to leave. So conservation of charge, and if you apply conservation of energy, then you are able to get the KVL. So based on that, I have written this kind of differential equation, and I hope that this is pretty easy to understand. So you can see that in this particular loop current is IL. So I can write R2T, because that is varying with respect to time varying resistor, and IL, and after that L di by dt. And you can see that whatever voltage across here, so same voltage is basically reflected here, and that I have you assume as a VC. Due to that reason, this equation comes into picture. And after that, I am going to apply here basically that KCL I am going to apply Kirchhoff's current law. You try to see here that I have three different kind of current. One current is basically flowing through this, one current is going to flowing through this, and after that one current is going to flow following through this, and I have certain kind of current here. So how to write all current? And it is easy. You can see that here I have voltage minus VC plus E1 by R, and after that this kind of thing. So please check it. This is pretty easy. So I have written everything. So here VC voltage, so I can able to write that what is current that is going to flow through this particular element. And I hope that this kind of things is Q equal to CV. So dq by dt equal to cdv by dt, and this is through nonlinear resistor, and this particular current IL is going to flow through the inductor, and this is the current that is generated from this particular source. So in this way I can able to land up to the differential equation. So I have two differential equation. I have already told you that why only I have two differential equation. So physically I can also able to interpret it. Now you can see here that I have some kind of non-linear relationship here, and due to that reason this whole system is some kind of non-linear system. So what is meaning of non-linear system? Those class of system which is not going to satisfy the property of superposition. But that is not the case, because linear system is also characterized a class of nonlinear system, and due to that reason we are telling that nonlinear system is those class of system who is not necessarily a linear. So I have generalization, and if you try to capture this generalization, then I can able to write different set of the equation. So suppose first case. So in first case, what I am going to do, I am going to disconnect the nonlinear resistor part. It means that I am going to remove the from the circuit. I am going to remove this particular element. So you can just remove the particular element, and after that again you have second order model, and you can see that you have one time varying term here. And if you write the differential equation, so please try to do exercise by yourself. Just you can put the nonlinear part equal to 0. It is possible to write differential equation like at xt plus bt into ut, where x belongs to R2, and after that ut belongs to R, because I have just one voltage. And if you see this, this is 2 cross 2 matrix, this is 2 cross 1 matrix. So please check it. And after that I can also do generalization that if this system is represented like this, so I have, it might possible I have n number of state in some general system, that is x1 x2 up to xn, and each and every quantity is some kind of either real number or real valued function or something that is related to real. So due to that reason I am going to write Rn. And similarly I can define that for general purpose ut belongs to Rm, so m number u1 u2 and um. So this system, whatever this system is called linear time variant system or linear time varying system. So this is called linear time varying system. This will satisfy the property of superposition, and it is pretty easy to check that here x1 1 is here. Now let us try to see the whole system. If you see the whole system, if nonlinear resistor is also there, then I cannot able to represent like this. And due to that reason some function kind of notion comes into picture, and this is the generalization. This class of system is called force system because forcing function is here, and after that I have time varying term is here, and due to that reason this is force time varying system. And here for generalization again x belongs to Rn, u belongs to Rm, and this function, now whenever we are talking about system that represent function, so I am telling that t I am going to select from positive time, x I am going to select from Rn, this is Cartesian product, and Rm, and that map to Rn. So in this way I can representing this function. So what up to here what we have seen, if you remove the nonlinear resistor, then you have linear time varying system. After that, if you are not going to remove anything, then you have force system, but that is time varying because explicit time varying term, and that is reflected from RT is present. Now what you can do, that you can just replace R2 by some kind of constant resistance. Then automatically this T, explicit dependency of T, is now no longer comes into picture. And after that what happens, I have this kind of differential equation, and again x belongs to Rn. Now you are able to understand what is meaning of Rn, and this is Rm. And after that this system is called force system because forcing function is here, and this is time invariant, means explicit dependency of time is not present here. Now let us try to see the other case. You can just remove the voltage source. So if you remove the voltage source, so now what happens, that my circuit still has some kind of time varying resistance, and due to that reason now I have system, and but there is no forcing function, means no voltage, and due to that reason this kind of circuit comes into picture, and this is called, this class of system is called non-autonomous system. So again here you can see that this xt is belongs to Rn, and here this function is now has two argument only, r plus Cartesian product Rn, and that is mapped to Rn because that is differentiation of x. Now if you put e equal to 0, and time varying resistance also as a some kind of constant, then you land up to this class of system, and this class of system is called autonomous system, and generalization of that is x belongs to Rn for this particular circuit, n equal to just 2, and function here that become more simpler than Rn to Rn. So in this way I can able to define lot of different class of system, and you can see that I have force system and I have autonomous system, I have non-autonomous system. So these kind of terminology I am going to use inside this literature. And after that you can see that I have talking about LTV system. One more class of system is called linear time invariant system. So if in place of time varying resistor, if you put some kind of resistor which is constant, and if you remove the nonlinear element, then AT is just converted as a BT is just converted as a B, and that is called linear time invariant system. So these kind of terminology, so try to understand the terminology. So I have either autonomous system, non-autonomous system, force system, linear time invariant system, linear time varying system. Now let us try to understand that why in order to define optimal control people are using state variable. So having the mathematical model in state variable form is more convenient. And why that is more convenient, you try to understand why. I have taken some examples. So you might have seen that in classical control we are expressing everything in frequency domain, and after that transfer function comes into picture. It is possible to show that whenever we are trying to simulate that kind of polynomial or try to calculate the root of polynomial using some kind of computer system, then some problem comes into picture. So in order to show that, what I am going to do, I am going to consider one transfer function, and that is represented by this polynomial, and after that I am going to see the roots. So you can see that root is -1, -2, -2 and -2. After that what I am going to do, I am just going to do the 10% variation, and I am going to change 7 by this and 18 by this particular numbers, and after that you can see that all other quantity remains the same, and try to see the effect. So if you see the effect, so initially everything is just a real number. Now automatically complex number comes into picture. So by certain variation, what you can see, you have observed that real number is transferred into complex number. So, and most of time what happens, whenever we are doing input something 7, we are input to the computer, so exactly that is not input as a 7, some approximation 6.999 or some approximation that is going to enter. So what happens, I cannot able to exactly know the value, and due to that reason people are avoiding this kind of, means whenever I have something in frequency domain or some kind of things that is represented by some kind of polynomial, then first what people are doing, they are converting that into the some kind of differential equation. And in order to solve differential equation, we have several excellent algorithm that is available in several software, or I can use several different numerical technique to solve that. And due to that reason, for implementation point of view, people are prefer the state space representation. After that you can see that a state space form provide a unified framework for the study of nonlinear system as well as linear system. But if you see the frequency domain approach or other approach, that is just limited for the linear system. So that is the another beauty, that using one framework you are able to understand the large class of system. And after that, for theoretical investigation, it is possible to show that I can select those kind of state variable which has certain kind of physical meaning, some kind of a strong physical motivation, and due to that reason also we are expressing the control problem in terms of a state space form. And due to that reason, whatever problem I am going to consider in this particular course, optimal control course, that is expressed in terms of a state space model, either that is represented by continuous differential equation or some kind of discrete difference equation. Now let us try to come to other component that is very important, and whenever we have some kind of system, we are basically talking about that concept. So somehow we are telling that, okay, now I have certain kind of system, and this is the most generalized one. So I have this as a non-linear system. After that, you can see that this class of system is also called force system, and I have here time varying term is explicitly present. So if you develop theory for this class of system, automatically that is applicable for almost all class of system. Due to that reason, whenever people are stating some kind of theory, they are taking more general class. So I am assuming that I have some initial value of the state, and after that you try to understand this notion. What we are telling that most of time in practical problem, my state cannot take all value. So even if x can be anything, but that is limited to some domain, and that domain is D, and due to that reason I have written like this: xt belongs to D, and that is subset of Rn. So whole space is Rn, but my interest is only in this particular space. And similar kind of a story that is associated with the and whenever I have limitation, then I can write that this space, product space, we are telling, that is basically map from this to Rn. But even if you can assume x is limited, but I have no restriction on x dot, and due to that reason that map to Rn. That is the meaning. Now let us try to understand the definition of controllability, and before going to talk the definition of controllability, we try to understand the problem. So what we are telling that I have some kind of physical system, and x is certain kind of variable. So I have taken the example of that car, and what is my aim? I want to go from one point to another point by using car. It means that there exists certain kind of control action such that I can able to move my car from one point to another point. That is the meaning. So that is not always possible. Always there exists certain kind of restriction or some kind of system. Means for some system it is possible to show that I can design some kind of control action such that I can move from any point to another point. But for some system this is not possible. So I will give several examples in this context, then you are able to understand that why this notion is very important. So what we are telling that if there is a finite time, that is t1, and a control which transfer the state x0 to the origin at x1. So I have what I am telling that I have certain kind of system. Initially I have here x0, and I want to move to the equilibrium point. So equilibrium point xt equal to 0 in some kind of finite time t1. So I have started my experiment at t1, t0, and I want to move to t1 in finite time. Then we are telling that the state x0 is said to be controllable at time t0. If all value of x0 are controllable for all t0, then system is called completely controllable. So this is the definition. Now let us try to see that why this definition is relevant for optimal control problem. So what is objective of optimal control problem? Our objective to transfer a system from an arbitrary initial state to the origin, most of time origin or some other point that is not the origin, that is also possible. And in between, whenever we are doing this, we have to minimize the some performance measure. So we are defining the performance measure In previous class I have told you that what is meaning of performance measure. In next class I will also I will give you the more brief overview how to select performance measure for some particular class of problem. So that is the aim of optimal control problem. So in optimal control problem also I have to move from one point to another point, but only one extra component is involved, that is performance measure, and we have to minimize that. So again, controllability of the system is the necessary condition for the existence of solution, because we have to move from one point to another point, and due to that reason we have to check the controllability. If you see the controllability of nonlinear system, then that is little bit difficult. There is means if you talk in terms of necessary and sufficient condition, then that is very difficult to extend for general class of system. But at least for linear time invariant system, we have some kind of clear cut condition, or some kind of condition that is necessary and sufficient condition. You can tell that suppose if I have some linear time invariant system, then I have to just check the this particular matrix, and this matrix is called controllability matrix. And here you can see that I have this A is called system matrix, B is called control input matrix. So by choosing these two matrix, I can generate this matrix B A B A square B up to n minus 1 if number of state is n. So we have to check this matrix, and if rank is n, then I can tell that it is possible to select any state, and after that I can move to the origin in finite time. That is the meaning. Now similarly, another notion that is related to the observability of system, and this is somehow connected with the output. What happens that most of time I have limited number of output, or output is expressed in terms of some function. So now question is that is it possible to know the other unknown state from the notion of output and whatever model that is provided to us? It means that I have finite number of initial condition, and from that initial condition I am going to find the all initial condition of the state variable. That is the meaning. So in this process, since control is not involved, so either you can put control or not put control, that doesn't matter. So now definition of observability: if by observing the output yt during the finite time interval t0 to t1, the state t0 x0 can be determined. So just by observing yt in this time interval t0 to t1, if I am able to understand the initial condition, all initial condition x t0 x t0 equal to x0 I have defined, then x0 is said to be observable at time t0. If all states x0 are observable for every t0, then system is called completely observable and simply observable. So these are the definition. But what happens that in this particular course I am assuming that all states are available, so there is no need to worry about the concept of the observability. But it is possible to show that one can also solve the optimal control problem if I have just output information, and at that time these concepts are equally important. And now you try to see here that I have again taken LTI system. I have again comment that for general class of system, concept of observability is giving necessary and sufficient condition is difficult. But for particularly for LTI system, by checking this observability matrix, one can talk about the observability of system. Means if I know the output, it is possible to understand the all initial condition of the state. And if I know the initial condition, and if I know the ut input, then I can obviously talk about the all future behavior of the system. Now in order to understand the controllability, I have already recorded the lecture, 3 lectures on controllability and observability. All kind of mathematical treatment are available. So those who has interest, please go through that lecture. So here I have just written the definition, and after that, using one example, I am going to clarify the concept of observability and controllability. So let us try to take this simple example. So I have some kind of linear time invariant system. I have taken x1 dot equal to 2x1 plus u, x2 dot equal to x minus x1 minus x2 plus u, and y equal to x2. So this is my system, and one can also see that this system can be represented by this kind of block notion, where this is the integrator. So x1 dot is coming, and after that we are getting x1, and x2 dot is coming, and after that we are getting x2. So I hope that this is not very difficult block diagram to understand that how basically this particular differential equation is represented by this. And after that I can also represent that equation in matrix form. So here basically x is nothing but x1 and x2 I have defined like this, and after that u is just belongs to R, and I can represent A as a this, B as a this, and C as a this, because we have already seen that in order to check controllability and observability, I need these three metrics. But in this particular example, I will give you the another overview also. If you do not believe on the Kalman test, this is called Kalman test. Is it possible to check the controllability and observability or not? Because if you understand this kind of things, then you are able to extend the idea of controllability and observability for nonlinear system also. Due to that reason, I am going to discuss some more criteria. And here you can see that first, since this is LTI system, so everything is very simple. So I have to just check the rank of this matrix. If you check the rank of this matrix, then you can see that same data is repeated here. So obviously this matrix is rank deficient, and due to that reason system is uncontrollable. And similarly, now I have to check the observability matrix, but here I have full rank, and due to that reason this system is observable. So it means that this system, whatever system I have represented here like this, so this system is not controllable but observable. So that is the meaning. And after that, now let us come to the another criteria. So one can able to see by the linear algebra actually what happens, that this criteria is based on the following simplification. Whenever you have system like LTI system like BUT, XT and BUT, it is possible to show that if initial condition, you can take for time being initial condition equal to 0, but same kind of result one can talk even if we have finite initial condition. And if you convert this equation in some kind of frequency domain using some kind of Laplace transform, it is possible to show that I have some kind of relation between input and this kind of output. So what you can do, you can apply Laplace transform, and after that you try to draw the relation between input and output. So that is just exercise for you. And after that, what we can see that somehow this kind of matrix comes into picture. As Si minus A inverse B kind of matrix comes into picture. So by checking this matrix, if some cancellation occur, then system is uncontrollable. So that is the meaning. So what you can do, you can apply Laplace transform. So this is the exercise, very simple exercise. And after that, now you have to just check that this particular matrix, is there some pole zero cancellation happens or not. If that happens, then system is uncontrollable. If not, then system is controllable. So that is pretty easy. And after that, whatever cancellation, you can see that in this particular problem, these two things, pole or zero, that is going to cancel out, and due to that reason uncontrollable mode is associated with this, means I cannot able to track that particular mode. And similarly for observability, if you do that kind of calculation, this kind of matrix is involved, and again you have to do same. And since no cancellation occur, and due to that reason, this system is observable. So this is the another way you can able to check. Another way is basically based on the transformation. So this is very good way. So for again linear system, this is easy, but for nonlinear system you have to do some kind of involvement. So what you can do, first you can calculate the eigenvalue, and corresponding to each eigenvalue you can calculate the eigenvector. So I hope that you are already all are a student of means master or PhD, so you are able to understand that, or even if you are a student of bachelor final degree, you are able to understand that how to calculate eigenvalue and eigenvector. So you can calculate the eigenvalue and eigenvector. After that, by calculating eigenvalue and eigenvector, what you can do, you can form some kind of model matrix. So model matrix is nothing but matrix of independent eigenvalue, eigenvector, and after that what you can do, using that model matrix you can perform some kind of transformation. So I have defined this kind of transformation, and after that it is possible to show that if A is, if system matrix have all independent eigenvalue, then all M inverse AM is diagonal matrix. So now in order to check controllability, just we have to worry about this M inverse B, that if M inverse B has all non-zero row, then I can tell that system is controllable. Means control signal is explicitly going to appear with respect to all transform state. So in order to do transformation, first you can calculate the eigenvalue and eigenvector, and with eigenvector you can form this kind of transformation, and after that just you can check that all M inverse B has all non-zero rows or not. Similarly, you can see here that you have to check that this particular matrix CM has all non-zero columns or not. If that has all non-zero columns, then you are able to tell that system is observable. So in this way I am going to apply this technique, and why these techniques will work. So I have written in remark, to verify the first statement, note that if the ith row of n inverse B is 0, then input U has no effect on the corresponding model response Qi. And if I do not able to effect Qi, then I cannot able to control it. Similar kind of statement we are able to understand here. To verify the second statement, note that if the ith column of CM is 0, then model response Qi will never be included in the output, and then mod is not observable. So in this way I can also able to understand. Particularly for nonlinear system, transformation is not so easy. So at that time you have to do transformation, some kind of nonlinear transformation, and at that time you have to again form certain kind of criteria such that these two conditions will comes into picture. Now let us try to apply this kind of criteria for again whatever criteria we have developed, to check that our result remains consistent or not. And you can see here M inverse B, if you calculate, then again this one element becomes 0, due to that reason that is uncontrollable, but here all element is non-zero, and due to that reason this is observable. So from, and if you see the transform coordinate frame, then things become more clear. So if you have nonlinear systems, so try to do some kind of transformation. Particularly some class of linear system, it is possible to show that using Lie derivative or Lie bracket, it is possible to convert that system like this. And again one can talk about the controllability and observability. So that is somehow consistent with respect to linear system, but class of that system is very much limited. And here you can see that there is no explicit control is appear here, and this equation is, although that is stable. Why I am telling this is stable, you try to understand like this. Q1 is belongs to R, so this is some kind of real number, so you can take anywhere Q1, and after that q1 dot is minus q1. So if q1 is positive, then q1 dot is negative. If q1 is negative, then q1 dot is positive. So finally I converge to the equilibrium. So due to that reason, q1 is always tending towards 0 as t tending towards infinity. Obviously I cannot converge to the origin in finite time. So I am telling that I have no control on q1, but I have obviously control on q2, and due to that reason you might have seen that our system become uncontrollable. But output, both states are appear, and due to that reason system is observable. If you draw the block diagram of this system after transformation, then you are easily able to understand that control is no longer going to appear across this block, and due to that reason this block is not controllable. But at output y, you can see that q1 and q2 both are appeared, and due to that reason system is observable. So in this way I can able to talk about the controllability and observability. One more thing, even if you don't know the criteria, but if you have clear cut understanding, then you are able to talk about controllability and observability. So I have taken this complicated system here. This is fourth order system, but you can see that in this fourth order system, if you check this x, so basically x is nothing but x1, x2, x3 and x4. Particularly if you come to this particular row, here you can see that control equal to 0, and after that I have this kind of equation. So, and this equation as x3, similarly this is one dimension, so now I can interpret like this. You can take x3 as a some positive number, then what is x3 dot, that is again positive, so we are diverging like this. Similar kind of situation comes into picture if you are starting from here. So finally I will diverge, and due to that reason, by seeing the equation I can also talk about the controllability. Similarly, I have taken another example in order to understand the observability without checking any kind of criteria. So you can see that from the example that x1 and x3 are not included, all are 0. It means that not included inside the output directly. So we have to see that there exists indirect connection or not. But if you see that, then two states are also decoupled. If you see the equation, particularly these two equations here, that the two states are fully decoupled, and after that I am talking about this and this, and after that what happens, that due to that reason it is possible to show that x1 and x2 are basically not observable. So they are not able to carry the information of x1 and x3, and due to that reason x1 and x3 are not observable. So basically in this way I am able to talk about the controllability and observability. So now let us come to the conclusion. What happens that whenever we have certain system and I have to design optimal control system, then first step we have to do the mathematical model in state space form, and basically I have to select model that is not very much complicated, otherwise optimal control become very difficult to analyze or very difficult to apply. After that, once mathematical model comes into picture, then I have to check that that particular system is controllable or not. If that is not controllable, then I cannot design any control. So if I am not able to design any control, then how I can talk about optimal control? And if I have fewer number of state variable, then I have to check that system is observable or not in order to proceed further. Because if system is observable, then from fewer number of output I am able to understand the initial condition of all states, and then again we are able to solve the optimal control problem. And in this whole course I am going to talk about either linear time varying system, time invariant system, or some kind of autonomous system and some kind of non-autonomous system. So with this remark, I am going to end the today's lecture. So thank you very much.